Thank you for having me today. I'm going to leave my camera off to help with this. Today I'll actually talk. This is a perfect ordering because this is I think a good follow-up for Olivia's talk. Olivia talked about some spatiotemporal dynamics, the consequences of some spatiotemporal dynamics in recurrent spiking networks in a balanced state. And I'm actually going to be talking about the exact same type of spatiotemporal dynamics in exactly the same bifurcation. The only difference is I'm going to be talking about the what causes the bifurcation and the stability analysis, whereas Olivia was talking about the sort of consequences of it. So this was work done with my former PhD student, Ryan Pyle, who did all the sort of heavy lifting for this. So I'll be talking about recurrent networks of spiking neurons. So we have an excitatory and an inhibitory population, integrate and fire type of models with delta synapses. The equations are on the left, but really you can just think of it as a recurrent network of spiking neurons. A lot of you know what it looks like. And at the moment, sorry, my dog is barking at the background to top everything else off. And we consider spatially homogeneous input to the map right now, because we want to focus on dynamics that arise intrinsically in the network. We'll also be arranging these neurons uniformly on a square domain on a lattice with connection probabilities that decay with distance. So they decay like a Gaussian with distance. So the connection weights depend on neuron type and the probabilities depend on distance. A lot of these details aren't so important for the things I'm going to be talking about, but all the simulations look like this. So first, I'm going to start off just by showing you what the simulations of this network look like. So in these animations here, the x-axis is the x direction in space, and the y-axis is the y direction in space. So this is a 200 by 200 grid of neurons, so 40,000 excitatory neurons here that we're looking at. And I'll start with a simulation where excitation projects more broadly than inhibition. So the excitatory connections fall off more slowly than inhibitory projections with the distance between neurons. And we see this nice sort of homogeneous spiking state. So even though this is a spatially organized network, it's receiving spatially homogeneous input, and the spiking statistics are spatially homogeneous. Then as we broaden inhibition little by little, so this is making inhibition just a little bit broader, the same type of changes that Olivia was talking about, we see these spatiotemporal dynamics start to arise. We make inhibition broader still, and we see sort of more coherent, sort of interesting looking intricate patterns. And even broader inhibition, now we see these sort of frozen patterns in space, these little disks that are frozen in space. So I wanted to understand sort of what's going on, what's causing this, this pattern formation in these spiking networks. So we first noticed this phenomenon, actually, I first noticed this when I was doing my postdoc with Brent Doran on 1D balanced networks. So now arranged on a one-dimensional space instead of two-dimensional space, but everything else more or less the same is what I'm looking at here. So we reproduced this phenomenon, or we saw this phenomenon in our simulations. Whereas the sort of quenched patterns, which was the last animation I showed there, and in 1D space, it kind of looks like this thing on the left. We captured those. We showed that those arose from a Turing bifurcation. These traveling wave solutions, which are analogous to the sort of spatiotemporal patterns in 2D, are stability analysis that we did using a neural field equation was not able to capture these dynamics. So I set out with my PhD student several years later to try to understand these dynamics better. So first, let's think about how to analyze the fixed points and the stability in these networks. Recurrent spiking networks can be a little bit tricky to analyze very rigorously. So we take what's called a diffusion approximation. So the idea is to treat the input. So I here is the input to a neuron at location X and time T. Remember, X is a two-dimensional vector here. It's a vector in two-dimensional space. There's an excitatory and inhibitory component. So the little arrow on top of the variables tells you that there's an EI component. Boldface tells you that there's an XY component. So it consists of a mean input, and then we approximate the variability around that mean with Gaussian white noise. So this is just an approximation. Of course, the real statistics of the noise they receive is not Gaussian white noise, but it tends to work relatively well in a lot of settings. And the mean and the variance now can themselves depend on space, right? So there's a spatially dependent mean and a spatially dependent variance. If the rates, or if you assume the rates depend on space, the firing rates, then the mean and the variance can be written as convolutions of some kernels with the rate. So this is actually a matrix of kernels because there's an EI component. So you get an equation that looks like this. If you then now plug this into an ODE for the rates, sort of a standard rate model, you get what's effectively a neural field equation, right? So this would be exactly a neural field equation that we're used to using if there were no variance term, right? You'd have some nonlinearity phi, and then the mu is actually just some integrals across space. So this is a type of neural field equation. Now we just have an integral for the mean and an integral for the variance. So this is a integro-differential equation in two spatial dimensions, but there's also two dimensions in our R, an E and an I component, right? So in the case that the input to the network, the external input to the network, is spatially homogeneous, in that case, you have a spatially homogeneous fixed point as well. We'll call that R naught. So it has an E and an I component, but it does not have an X component, right? So there's one E firing rate, one I firing rate that applies across all of space, and that's a fixed point. So we're interested in the stability of that fixed point. That's what's broken in those animations I was showing you. So if you start with this integro-differential set of integro-differential equations, you can linearize and take the spatial Fourier series. Here we're using periodic boundaries for simplicity in space. And basically you get a linear ODE at each spatial Fourier mode. There's actually two spatial Fourier modes because it's two-dimensional space, but that's not so important. And you get a Jacobian matrix at each spatial Fourier mode, right? We'll call that J at N, right? So this tells you about this is a perfectly mathematically sound way to analyze the stability of fixed points in these integro-differential equations. So if we do that, we get a spectrum of eigenvalues that look like this. So in this case where we saw stability of the homogeneous fixed point, indeed we see eigenvalues with purely negative real part. So things seem to work well. If we go all the way to this case where we get these sort of quenched patterns, we see eigenvalues arise with positive real part and zero imaginary part. So this is a sort of a prototypical Turing bifurcation that you see in this case, and it gives rise, as expected, to sort of spatially quenched patterns. Now, of course, because of noise in the system, these little circles will actually gradually, slowly diffuse around. If we had heterogeneous spatial input, it can quench them. But that's a lot different from these patterns, which are intrinsically sort of moving around through what looks to be more of a drift term than a diffusion term. But interestingly, this stability analysis doesn't capture the instability that we sort of see empirically here. So the stability analysis gives all eigenvalues with negative real part. So it predicts that this fixed point is stable, but there's clearly something going on in the center plot that does not look like this left plot. So what's wrong with this picture? Why can't we capture these dynamics with a stability analysis? So I was thinking about this with my former PhD student, Ryan, and also after some conversations with Bart Ehrmantraut, kind of pointed me in the right direction of what to look like, what to look at. We started thinking about this, and we know that firing rate dynamics actually have a history dependence that's not captured by the simple differential operator, this differential equation. Another way to say this is firing rates are the system of firing rates, if you view it as a sort of a system in the sense of physics, it is time invariant. There's nothing special about one point in time versus another point in time, but it's not a dynamical system. You can't predict its future based on its present state. And that's because there are some sort of hidden dynamics coming from the membrane potential that cause that to happen. So that causes a sort of history dependence that is not captured by this ODE, right? So one approach to doing this is modeling analyzing the stability of the membrane potentials directly instead of the firing rates. but we chose a different approach. We're going to stick to firing rate space, let the membrane potentials remain hidden, but we're going to try to think about how do we perform stability analysis on a system that's time invariant, but it's not a dynamical system. So it has some delayed effects in it. So if you're familiar with the analysis of delay equations, basically delay equations, then this might look familiar to you. If you're not, I'll sort of walk through the basic idea. So the basic idea to do the stability analysis is we take our firing rates at the fixed point, and we apply a small perturbation. You can see that in the picture here. This small perturbation then echoes through the system to cause a perturbation in the mean and the variance of the input. Now, this is a totally linear operation, and it has no time dependence because the mean and the variance are related exactly to the firing rates at a particular point in time. But then the mean and variance perturb the firing rates in a way that does have a time dependence. Through what are called the susceptibility functions, or sometimes linear response functions, which I'll call A for the mean and B for the variance. You can compute these through a Fokker-Planck formalism, the same formalism we use to compute the phi, the mapping from the fixed point mean and variance to the fixed point firing rate. Don't have time to go into the details there, but I'm happy to talk offline about it, or you can see our paper. So now now we actually have an integral across time that gives rise to this perturbation, this effective perturbation in the rates. So putting all this together, we have a self-consistent equation for a perturbation. So this gives you sort of how a perturbation to the rates echoes through the network. It has a integral across space and an integral across time. So we have two-dimensional space and time. We can take the spatial Fourier series and the temporal Laplace transform, and we get that for this equation, the second to last equation here, to be satisfied, this last equation needs to be satisfied. This function that we're setting equal to 0 is sometimes called an Evans function. And the hat here is the Laplace transform of A. The tilde is a Fourier transform in space. So Laplace in time, Fourier in space. And we need to solve this at all lambda and all pairs of Fourier modes N1 and N2 that are in this vector N. And wherever we find a solution, the associated lambda is an eigenvalue, and the associated Fourier mode is an eigenfunction. So this type of analysis was also presented in this paper by Ledoux and Brunel, but without space. So they looked at this in a non-spatial system. So you can view this as a generalization of that approach to a system in space. Okay, so what happens if we perform this analysis? Now things seem to work out. So in the case where we see the homogeneous fixed point sort of looking stable, we get all eigenvalues with negative real part. So the eigenvalue spectrum looks a little more interesting here. And then as we broaden inhibition, we start to see these eigenvalues cross the imaginary axis here, and we get some eigenvalues with positive real part. Importantly, these eigenvalues with positive real part do not have zero imaginary parts. They have non-zero imaginary part. We get a conjugate pair of eigenvalues. And this is what's called a Turing-Hopf bifurcation. It's sort of a mix between a Turing bifurcation, which is where you get, which is what happens when you have eigenvalues in these spatial systems that cross the real axis, and a Turing bifurcation where you get eigenvalues that go from negative real part to complex conjugate with positive real part. And this gives rise to spatiotemporal patterns like you see in this picture. You can, if you look at the sort of spatial and temporal frequency of these patterns, you can get some information about those from the eigenvalues here. So the unstable eigenmodes, which are Fourier values, predict the frequency of the spatial frequency of the moving dots or whatever you see there, the traveling waves that you see there. You can view these sort of as interactive traveling waves, traveling in different directions, and they're colliding all the time. The noise is sort of pushing them together and causing sort of a more complex picture than you see with just traveling waves. Let's see if there's a question in chat. Okay. I'll answer those questions later. I just wanted to make sure it wasn't about my internet connection or something like that. Okay, so that's all well and good. We get these pattern formations. So this is, I think, mathematically a cool, what I thought was an interesting thing. We were able to, first of all, show that you can't capture these dynamics with standard rate equations because of this history dependence. And then we were able to describe them using this other formalism that's often used for delay equations, even though we don't explicitly really have a delay equation here. So my Ryan, my former PhD student, took this a few steps further. I wanted to look at the sort of dimensionality. This is something that Olivia talked a lot about. We took it a slightly different direction, but similar to what Olivia was talking about, the dimensionality and sort of complexity of these dynamics. So in the stable case, what we did is to measure this, we gave a global input to the network. So just a sine wave. All neurons receive this sine wave input, sort of pushing the rates up and down. And in the stable case, we saw the rates. So then we read out the rates. So we set up a grid of, I think, a 10 by 10 grid of neurons or something like that, and average the rates of those neurons. And that's what you see. Each one of these rainbow lines here is one of these readouts, right? So it's a local readout of the firing rates. We saw they sort of tracked the input. And so then if you try to explain the variance in these local rate readouts, there's 100 of them. We saw that most of the variance is explained by the first principal component, because basically what's happening is all the neurons are doing the same thing, this sinusoid, with some noise around it. So the noise is distributed more evenly across the other principal components. There's 100 of these principal components, I think, if I remember correctly. Or maybe there's 10 of them, I kind of forgot. No, there's more than 10. I think there's 100. Then in the unstable case, there's definitely response. So the input does affect the network, but not all the neurons are doing the same thing. Some go up during the up phase of the input, some down during the down phase, some up during the down phase, et cetera, et cetera. And it takes more principal components to explain what's going on here, right? Okay, so this could be interesting because this could be used for example, performing high dimensional computations. However, what we saw is that these dynamics are not reliable from trial to trial. So what we did here is we did the same exact simulation, the same exact experiment, except we gave the same global input to the network 10 times. So we repeated the same simulation 10 times, each with a different sort of initial condition at the beginning. So the network's doing the same thing, but the noise in the network is randomly sampled, right? And what we see is that on every trial, each principal component is doing something totally different, except for the first one that's more or less just tracking the input with some nonlinearity applied to it, probably due to some sort of shunting. But all the other principal components, whereas they do explain some of the variability in one trial, that's not shared across trials. So then we realize what's going on here is that there's a pattern, symmetry breaking bifurcation, and on every trial, it sort of breaks in a different direction. So every trial is doing something totally different. If you think about these spatiotemporal patterns, they're arising from breaking the stability of a homogeneous fixed point. Would you break the stability of a homogeneous fixed point, sort of anything could happen. So every time something different is happening. So we modified the simulation by applying an input that varies in time and space. So now different neurons receive a different intensity of the input, and I think also a different polarity, a different sign. And now we get these intricate dynamics. So every principal component is doing something different. So we get this high dimensional dynamics, rate dynamics, but it's preserved from trial to trial. So all the trials seem to be doing the same thing. So why might this be important? So if you wanted to perform a computation with a network like this, one idea, sort of a simple idea behind performing computations with recurrent networks is reservoir computing. The idea is you treat the network like a reservoir of dynamics and you train out the features that you want. But for that to happen, of course, you need them to be high dimensional and reliable to be able to get what you want out of it. So what we did is we trained some readouts from the network, and we tried to get those readouts to match a target output. So the target output looks like this thing in red, the black dashed, and we wanted to train the readouts. So train the weights of these readouts to match the target. And we gave the same input to the network 100 times. This is a network input that varies across space and time, the same one I showed before. Well, actually in red here on the right is where it varies across space and time. In blue is where it only varies across time and not space, where we saw that it was unreliable. So only in the reliable case does the readout from the network actually match the target. You can see this visually on the left, and you can see that measured by the mean squared error on the right. So this shows that these spatiotemporal dynamics can be useful potentially for performing computations through this reservoir computing framework. But since it's a symmetry breaking bifurcation, the only way to get it to be sufficiently reliable to perform these dynamics is using a spatially heterogeneous input. And I think another kind of thing I like about this project is the sort of insights about performing stability analysis on rate networks, or on the idea that rate dynamics, I guess, are not necessarily dynamical systems because they rely on these hidden variables. That's important for performing stability analysis, but we should also think about it in terms of when we're analyzing data. It might not always be well informed to fit firing rates to a dynamical system model without hidden variables. So that's all I had to say, but I'm happy to answer some questions.
Thanks so much. Do you want to answer the question from Ernest?
Oh, sure. Yeah. Yeah, that's right. Yeah. So, Ernest asked if this failure of the firing rate equations to capture the Turing instability. So the firing rate equations capture the Turing instability, but not the Turing Hopf. So in the 1D equations, this is from this this paper in 2014. On the left is a Turing bifurcation, and this was captured by the rate equations, the neural field equations, because you see a positive eigenvalue at a particular eigenmode, and you can't see this in the picture, but this is the max real part, but the imaginary part was 0 here. But on the right, we see what's clearly an instability, this traveling wave, but the neural field equations predicted stability, the rate equations did. So this 2D and 1D results are exactly the same.
Thank you, thank you. I mean.
Thanks.
And you have one more question in the chat.
Sure, yeah. Okay, broader inhibition. Yeah, that's right. So with broader inhibition, you do get, the network is sort of better for reservoir computing, at least for our model. That's what we saw. So in the real world, inhibitory neurons, or if they're PV neurons, and excitatory are pyramidal. The dendrite length of most inhibitory neurons is shorter than most pyramidal neurons. So this, I think this is, so I'm not a huge expert in the field, but I think this is true of the visual system, is where this result is sort of most well confirmed, I guess. In the visual system, you probably don't want pattern forming dynamics. You're probably not doing something like reservoir computing. At least in my opinion, it kind of seems like this would be the wrong framework for modeling the visual system. I think looking at premotor cortex and prefrontal cortex and motor cortex, these generative, cortical regions that are sort of thought to be generative, generating dynamics for movement and things like that, would be more the place to look for these types of dynamics. And then the other thing I wanted to mention is that you can get similar spatio-temporal pattern forming dynamics that are also amenable to reservoir computing by instead of changing the spatial width of inhibition, changing the time scale of inhibition. So if inhibition is a little bit slower than excitation, you can get a similar type of bifurcation. So it doesn't have to be the spatial width.
Okay,
that's if the synapses are slower, or the neurons, really. Yeah, thank you.
Thanks again, Robert. Very interesting. We better try to go to the next speaker, and I hope he's here, Mark Goldman. I'm not sure I see him in the list of participants. Okay. Unfortunately, I've got a feeling he's not here, unless I don't know if anyone's got his phone number, if someone can ring him.
He is not in the other channel, so
yeah, yeah, there might have been.
Somebody could check the other room in case he's in the wrong room by mistake. I don't know.
I did it, and I cannot see him in the other channel.
Yeah, well, I know he was keen to chat, so I'm not sure. There's been some mix-up, I'd say.
Did you try sending him an email maybe?
I did, yes. Yep.
I could send him a text.
Yeah, if you could text his phone, that'd be great. See if he's.
And send the coffee also.
Yeah, early coffee time, right? I actually had a question for Robert, if while we're waiting, if that's all right.
Sure. Yeah.
Yeah, I mean, I'm curious. So you make the time invariance assumption, right? To look at the patterns. Do you have any ideas about how you'd proceed for shorter times? So without making that assumption of time equilibrium.
So I guess I'm not sure what you mean, because we're looking at a fixed point. So we're kind of assuming that the fixed point is we're sort of assuming stationarity of the noise, and then looking at a fixed point. So like in that sense, there's a sort of nothing really varying in time under stability, right? Or
right. Maybe I'm not understanding, because when yeah, exactly, because you're assuming time stationarity, right? I mean, it's the same.
That's right. Yeah.
Komplinsky did in his analysis, right?
Yeah. So we're assuming stationarity. We're assuming that the input is stationary in time, and then basically that the system has reached sort of a stationary equilibrium, statistically speaking, right?
Okay.
That all of the statistics are in their sort of stationary state.
Yeah.
So that's sort of implicit in this diffusion approximation, right? So we have maybe that's if I go back to there, that'll sort of get to the crux of the question.
It's very, by the way, it's very good work. I'm just trying to follow, because you can make diffusion approximation out of equilibrium too, right? I mean, I'm just wondering what would happen if you had out of equilibrium.
I'm not sure. Yeah, so if you were out of equilibrium, then I'm not sure how that analysis would go, because you still want to be looking at a fixed point. So you could maybe be looking at a fixed point in the mean, because the stability analysis, we're always assuming that the system is at a fixed point and then looking at a perturbation away from it and seeing if that perturbation is amplified, right, by the system. If some of the statistics, so I guess you could assume you're at a fixed point in the mean, and then have a non-stationary variance. Yeah, I'm not sure. I'd have to think about that, I guess. Yeah, good question.
I also have a question, if I may ask, while we're waiting.
Sure.
So I'm interested in this point that you mentioned about failure of neural fields to capture the Turing-Hopf. So in this case, do you have two populations, or are you just bunching the excitatory and inhibitory populations together?
We have two populations. There's a excitatory and inhibitory population. They have different connectivity statistics, and then in the neural field equation, there are two populations in the neural field equation as well.
Because one would expect that neural fields with two populations, they would typically give you these Turing-Hopf patterns and waves.
Yeah, so they can under certain conditions, but they don't capture this particular Turing-Hopf bifurcation. So they can capture a Turing-Hopf bifurcation, for example, by making inhibition slower than excitation in the neural field equation, and other things like this. So you can get Turing-Hopf bifurcations in a neural field equation with two populations, but it doesn't capture this particular Turing-Hopf bifurcation.
Thank you.
Because this one arises from this one fundamentally arises from the resonance in the spiking neurons. So that's the neural field equations completely ignore that resonance.
Yeah, so I see what, I mean, do I understand correctly? What you're saying is that if you look at the mean field equation don't look quite like what a neural field with two components would look like. Is that what you're heading towards?
No, the neural field does have two. Oh, I see. The mean field equations for the neurons, you mean?
Yeah.
Yeah. So if you had the problem is we don't have a sort of analytically rigorous mean field equations for the firing rates of the neurons, right? If you were to have one, then it would look different. So I think to capture this properly, what you would need to do is you would need to have mean field equations for the membrane potentials. And actually this analysis is sort of equivalent. So what we did is sort of equivalent to doing that, except the membrane potentials and this diffusion approximation. So you'd have basically a Fokker-Planck equation with a spatial variable. So you'd have a infinite system of Fokker-Planck equations. That's what the true mean field equation that would capture this phenomenon would look like. If that makes sense, you'd have a Vx, right? And then you'd have a equation for the probability density function of Vx. So that's comes into play. But stop me if I should stop. And these susceptibility functions, A and B, those tell you how the firing rate changes in response to a change in the mean or the variance, to a perturbation in the mean and the variance. They're kind of like a Green's function for the firing rate. But to compute these, we actually have to solve a Fokker-Planck equation involving the membrane potentials.
Yeah, I see. This is very impressive work.
We had the same phenomenon in Roxin and Brunel in 2005, where they have, I think, a single population of neuron, that the spiking neuron that is oscillating. And so the firing rate model converges to a fixed point, which is whatever stable, let's say. And so you cannot capture oscillations, and by adding a delay, like you did, they can capture all the dynamics of the spiking whiteboard. They can capture most of the dynamics of the finite size model that is oscillating.
Okay. Can you post a link to that in that chat?
Yes,
if you're able. Thank you.